All right, this is chapter 7, and chapter 7 and 8 are collectively returning back to chapters 2 and 4. So all the stuff that we did in kinematics in one dimension, we're going to do again now in chapter 7, except now instead of having things move in a straight line, we're going to have things move in a circular pattern. So all those various equations for velocity and displacement and acceleration, we're going to have those again, except the variables are going to be changed slightly to reflect motion in a circular path. All right? And then similarly in chapter 8, we're going to get into torques, and we'll treat those in a very similar way as we did in chapter 4 for Newton's law, second law, moment of inertia, or excuse me, inertia, acceleration, forces, torques, all that stuff. All right, so let's begin with chapter 7. In this chapter, we're going to discuss the rotation of rigid bodies. A lot of bodies are rigid. That just means that all the parts move at the same angular velocity. All the parts move at the same angular velocity. And that means that the parts do not move with respect to one another. So some examples of a rigid body, like let's say for example we just have a wooden stick, right? And it's rotating about that axis. That's a rigid body. We can think of a person rotating as a rigid body as long as they maintain their rigidity, that they're not moving their arms all around like, a dancer or whatever. But at any one moment, they're still a rigid body. Um, However, a non-rigid body would be like, for example, a rotating fluid, like a liquid, water or whatever. So if I have a fluid that's rotating, I'm going to have some parts of the fluid that are rotating at a certain rate, and then other parts of the fluid that are rotating at another rate. So that would not be a rigid body because different parts of it are rotating at different angular speeds or angular velocities. All right, now the axis of rotation is the axis about which the body rotates. And the same body can have several different or many different axes of rotation. So for example, the human body is a great example in how when you change the axis of rotation, or you can change the axis of rotation, and that's going to mean a lot about how the motion is pursued. So for example, if I have a person, I can move about several axes. Now I can rotate about an axis that just goes straight down through the middle of me, and that's going to be a fairly easy thing to do. Or I can move about an axis, going through my belly button, and that's a lot more difficult to do. So you can have many different axes of rotation, and we'll see that especially in the next chapter, chapter 8, how that affects your motion quite a bit, actually. All right, I want to define a few things. So just like we did in chapter 2, when we defined position, displacement, velocity, and acceleration, we're going to do that here now with angular quantities. Angular meaning that they're moving in a circular path. First of all is just the angular position. Angular position uh, is given by the unit theta. So when we talk about angular position, we're going to use the variable theta. The SI unit for the angle theta is radians. And other units include revolutions and degrees. The most commonly used degrees, and we'll use those of course, but we'll also use radians and revolutions, and we'll sort of use those interchangeably. Um, the conversion factor, oh, let me go back up. The conversion factor for these is that in one revolution, there are 360 degrees. So one revolution means all the way back to where you started, and that's equal to 2 pi radians. All right, so that's our position. Closely tied to position is the angular displacement. The angular displacement is just a change in position. If you remember before, we had displacement, and we said that was x final minus x initial, the final position minus the initial position. This is the same thing. We're just taking a difference in the positions. And so my angular displacement is just going to be theta final minus theta initial. Now, if you remember, for this, for our linear displacement, we said that right is positive and left was negative. So we need to do a similar thing here where we just set a standard for what is going to be positive and what is going to be negative. And in this case, our counterclockwise displacement will be positive, and our clockwise displacement will be negative. And so I always remember this because I always think of this like vast conspiracy to make clocks go the wrong way, right? So according to this notation, clocks would go in the negative direction, right? Because clocks go clockwise. And actually, you can go to some websites, and if you wish to do this, that's fine. But you can go to websites and you can purchase clocks that move in the counterclockwise direction, because that is the positive direction. So if you're going to go forward in time, then your clock should move in the counterclockwise direction. I'm not quite that dorky, but you might be dorky enough to go out and purchase one of these clocks that move in the counterclockwise direction. Nonetheless, it's very important that you get this standard right, or this sort of notation, that clockwise motion, clockwise displacement is negative, and counterclockwise displacement is positive. It comes up a lot in this chapter and the next chapter. All right, so that's our angular displacement. Oh, did I skip something? No. And now our angular velocity. Angular velocity we're going to call omega. This is the Greek letter omega, lowercase. It looks like a W, but it's not. It's an omega. And our angular velocity we can describe in a couple of different ways. We can... sorry about that. We'll define first our average angular velocity. Just like we did before, we had an average velocity, and that was our displacement over our time, or delta x over delta t. But now this is going to be delta theta over delta t. And we can also define our instantaneous. Just like we did with velocity in chapter 2, we can find the instantaneous velocity. If you're in calculus, as many of you are, we can define this as the limit as delta t approaches 0 of the average velocity, which is delta theta over delta t. So what we're doing here is we're just saying what happens if you let delta t get really, really small, infinitesimally small. Right? That's called a differential or a derivative, and that's equal to d theta dt. Right? So that's our instantaneous velocity, and we'll get into this, but all the equations that we used before for linear motion are also going to apply here. Now, if the angular velocity is clockwise, then the sign of the motion is negative, and if it's counterclockwise, then the sign of the motion is positive. So remember, clockwise is negative, counterclockwise is positive. Now, angular acceleration. We're going to use the Greek letter alpha to describe this. This is a lowercase alpha. Right, it looks like a fish, but it's not. And we can define two things, just like we did with velocity and just like we did with acceleration back in chapter 2. We have the average acceleration, which is going to be delta omega over delta t. And then we also have the instantaneous acceleration, and that's going to equal the limit as delta t approaches 0. So as you let the time interval delta t get really, really small for the average angular acceleration, this is just the definition of the derivative. So the instantaneous acceleration is the first derivative of the angular velocity. If the angular acceleration is clockwise, the sign of the motion is negative. If it's counterclockwise, it's positive, just like before. So remember, clockwise is always negative, counterclockwise is always positive. We can talk about the direction of angular vectors. This doesn't really come up much in this chapter, but I just want to present it here because it will come up next semester when we're talking about electric forces and magnetic forces. The direction of these angular vectors are given by the right-hand rule. The fingers wrap in the direction of the rotation, and the thumb gives the actual direction of the vector. Again, we're not really going to use this, and I'm not going to show it to you. You're not going to see it in quizzes right now, but you will see it next semester. So this is just a common tool that we use. It's called the right-hand rule, and we can use it to determine the direction of vectors when we're using a right-handed coordinate system, as we do in physics. Okay? Let's give you the equations. So I'm not going to go through and derive the equations. We did that in chapter 2. If you want to go through and revisit those, that's fine. I'm just going to write them out here. Now, with our linear motion, we had these equations. We had V equals V naught plus AT. We also had theta equals V naught T plus 1/2 AT squared. Those were our two kinematics equations. Sometimes you'll also see some other equations if you're looking at other books that just come from substituting one equation into the other. I'm not going to do that here. Now in angular motion, we have very similar equations where I'm going to let, excuse me, this shouldn't be theta. I made a mistake here. This should be x. Getting ahead of myself. In angular motion, we're going to let x be replaced by theta, let v be replaced by omega, and let a be replaced by alpha. It will take you some practice to get used to these new Greek letters, but it's important that you do because they'll come up on questions and what have you. And you'll need to know, well, the angular acceleration is alpha, or the angular velocity is omega, or the angular position or displacement is theta. Right, so we're just going to rewrite these equations. The derivations are the same as we did in chapter 2. This is going to be omega equals omega naught plus alpha times t. That's the angular velocity here is equal to the initial angular velocity plus the acceleration times time, the angular acceleration, that is. And then we also have theta equals omega naught t plus 1/2 alpha t squared. All right, so again, what we've done here is we've let x become theta, v become omega, and a become alpha. If you keep those things sort of connected in your mind, it'll help you a lot in this chapter, because really we're just doing kinematics just like chapter 2, the only with just a couple of differences where these variables are being replaced by their angular counterparts, and then also the directions are a little bit different, where we, instead of having left, right, negative, positive, we have clockwise as negative, counterclockwise as positive. Now we can also relate our angular and our linear quantities in this way. S which if I look at an arc, S is this distance, S. This is my angle theta, and that's my radius. S is equal to theta times R. V is equal to omega times R, and A is equal to alpha times R. I said this, but I'm not sure if you caught it, but the units for theta, the SI units for theta are radians. Right? Not that theta is rad, but the SI unit for theta is the radian. And so the SI unit for omega, you could probably guess, is going to be radian per second. And the SI unit for alpha is going to be radian per second squared. And so if I want to look at my units to sort of do my dimensional analysis here, for example, this is going to be radian per second squared times meters. And, this radian is not a real unit, so I'm just going to sort of erase it and sort of forget about it. And that gives me a unit of meter per second squared for the acceleration. In fact, often when you see like an angular acceleration or angular velocity, instead of seeing radians per second squared, for example, you might instead see just 1 over second squared. I don't usually use that notation, but sometimes you can do that. Sometimes that radians isn't really expressed as a unit, and that might be a little confusing. It is a little confusing to me too, but just don't really think of it as a real unit, but it is an angle. All right, let's stop there, and we'll pick up with that a little bit later.